Hello everybody, my name is Iman Esadi. Welcome back to my YouTube channel. Today I'm going to be starting a series for Organic Chemistry 2 to go alongside my Organic Chemistry 1 playlist. Now today we're going to be covering Chapter 14. This chapter discusses two very important instruments that are used for structure determination. And we're going to first start discussing infrared spectroscopy in this video in detail before diving into mass spectrometry in the next video. Now, as a first point of discussion, before we even start this lecture, I want to make a point of the difference between spectroscopy and spectrometry. Spectroscopy is the science of studying the interaction between matter and radiated energy, while spectrometry is the method used to acquire a quantitative measurement of the spectrum. Spectroscopy doesn't generate any results. It's simply an observation of the interaction between matter and energy. It's a theoretical approach of science. Spectrometry is the practical application where results are generated. Now, this will make more sense as we go through infrared spectroscopy and then mass spectrometry. But these definitions should be a good starting place for our discussion today. Now, let's get back to infrared spectroscopy. In order for us to have a conversation about infrared spectroscopy, why and how it works, we need to cover some fundamental physics concepts. And this way we can build a true understanding of this type of spectroscopy. So let's start at the basics. Now, experiments done in the early 20th century answered a really important question for us. Does light consist of particles or waves? And spoiler alert, the answer is both. And thus the idea of wave-particle duality was birthed, and with it emerged quantum mechanics. Now, experiments that proved this wave-particle duality included interference experiments, along with the photoelectric effect that Einstein developed, and other many experiments that really opened our eyes to this phenomena. Now, as a consequence of quantum mechanics and these experiments, it demonstrated that when you're dealing with subatomic particles, energy is quantized. That means that energy can only have certain discrete values. It's not continuous. And quantum mechanics is truly interesting in the sense that it shows us that things on the subatomic scale act kind of differently than macroscopic objects. You know, prime example here, things like electrons or photons, which are subatomic particles, act like both waves and particles. Now, we are familiar with a diagram that looks like this. The spectrum for electromagnetic radiation, from gamma rays to radio waves. Now, electromagnetic radiation can be viewed as a wave or a particle. Now, when viewed as a wave, electromagnetic radiation consists of perpendicular oscillating electric and magnetic fields. But when viewed as a particle, electromagnetic radiation consists of a packet of energy called photon. The photon is the unit of energy for light. The energy of each photon is directly proportional to its frequency. Now, electromagnetic radiation, to summarize, is a form of energy. It describes how electrically charged particles interact with each other and the magnetic field. I like to think of this from the perspective of a gym buff who is going to the gym, all right? And he's going to go ahead and look at his biceps. He's going to go ahead and he's going to grab two pieces of rope, one in his left hand, one in his right hand, all right, two pieces of ropes, and he's going to oscillate them and move them in opposite directions, and as a consequence, we're going to get this oscillating electric and magnetic field. All right, now this oscillating electric and magnetic field, right, this is our wave description of our electromagnetic radiation spectrum. Now, our electric magnetic radiation is going to travel at the same speed, the speed of light. But how we get this spectrum of different categories, from gamma rays to X-rays to UV to infrared to visible, microwave, radio, all this is because of a difference in wavelength of our electromagnetic wave and of frequency. So our electromagnetic spectrum is divided into different types based off of the different wavelengths and frequencies of each. They are all at the core electromagnetic waves consisting of oscillating electric and magnetic field, but because of the difference in wavelengths and frequencies of these oscillating fields, we get different categories in our electromagnetic spectrum, right? So one more time, all forms of light that we see in our electromagnetic spectrum has the same speed, the speed of light. The difference is in the frequency and wavelength. And let's define some important discussions. What is a wavelength and what is frequency? Well, the wavelength describes the distance between adjacent peaks of the oscillating field. So this is the definition of a wavelength. The distance between adjacent peaks. The frequency describes the number of wavelengths that pass a particular point in space per unit of time. How many wavelengths pass in space per 1 second, for example? Now, the equation that correlates wavelength and frequency is this formula right here. The speed of light is equal to wavelength times frequency. Now, our focus when we're talking about infrared spectroscopy is on a specific part of the electromagnetic spectrum, the infrared part of our electromagnetic spectrum. Why? Well, because we're talking about infrared spectroscopy. Now, remember, spectroscopy can be defined as the interaction between matter and light. When you shine infrared light on a sample or a molecule, what kind of interaction is happening? That is the question, the ultimate goal that we want to answer in our discussion of infrared spectroscopy today. So how does this actually work? Well, infrared spectroscopy is a chemical analytical method that uses differing frequencies of infrared light, all the light in the infrared part of our electromagnetic radiation spectrum, to detect predictable types of chemical bonds. Absorption of this energy radiation is going to cause vibrational excitation of groups of atoms within the molecule. Again, IR, infrared spectroscopy, specifically causes bond vibrations. Different kinds of spectroscopy can cause different kinds of responses, like electronic excitations or rotational excitations, okay? Infrared spectroscopy specifically causes bond vibrations. It's a vibrational excitation of a group of atoms within a molecule, and that is what we observe in the spectra that we obtain from infrared spectroscopy. Now, we see the absorption band excitation of bonds in the molecule in the infrared spectra we obtain. And because of characteristic absorptions, identification of functional groups is actually really easily accomplished. Now, we see that the vibrational energy levels for a particular bond are separated from each other by an energy gap. All right, so this is a diagram. All right, for some arbitrary bond, this is the energy diagram for it. All right, and each state is separated by an energy gap. All right, if you irradiate this with, say, infrared light, all right, if a photon of light possesses exactly the right amount of energy, all right, the amount of energy defined by this energy gap, then the bond can absorb the photon to then promote excitation, promote vibrational excitation. The energy of the photon is temporarily stored as vibrational energy until it's released back into the environment, usually in the form of heat. And it is this interaction, all right, the absorption of infrared radiation of the photon that promotes vibrational excitation, all right, it's this interaction that allows infrared spectroscopy to be useful and to allow us to identify functional groups present in molecules very easily, because different functional groups are going to have different vibrational energy diagrams, and different kinds of functional groups will absorb infrared light at different frequencies or wave numbers. Now, let's break this down one more time, all right? Just to really make sure these concepts are sticking, all right? So here we have a molecule, all right? This bond has an alcohol functional group. Awesome. We're going to just focus on this alcohol functional group right here. Let's draw the energy diagram for the alcohol group, for the alcohol bond, all right? Let's say this is arbitrarily the energy diagram, all right? The vibrational energy diagram for the alcohol group. Fantastic. Now, if we expose this molecule, this specific alcohol bond, right, to some IR radiation, we're going to observe that the vibrational energy for the alcohol group, all right, it's going to absorb that energy and it's going to get promoted to a higher vibrational state. All right, we're going to observe that the vibrational energy for the alcohol group is excited to a higher level. All right, and we see this in our absorption spectra because we get this peak, this signature alcohol peak. All right, when we see this signature peak of an alcohol group, we know the molecule has what? An alcohol group, a functional group, by the way, like an alcohol group, or even look at this carbonyl right here. Is it also, all right? These functional groups have a predictability. This predictability of where functional groups will show up on the IR spectrum is going to be the same every time. All right, and it's useful, this predictability of where functional groups are going to show up on the IR spectra, because we know that wavelength needed to excite the vibrational modes for particular bonds and bond types, and that makes infrared spectroscopy very useful. All right, so to reiterate, to make some concluding remarks on that discussion, all right, in an IR spectrometer, a sample is going to be irradiated with frequencies of IR radiation, and that frequencies that pass through are detected, and a plot is then constructed, and this is our spectra. Now, an IR spectrometer measures the percent transmittance as a function of frequency, and this plot that we get, this one that we saw right here, for example, is called an absorption spectrum. All the signals called absorption bands point down on in the spectra. Currently, the location of each signal is actually more often reported in terms of wave numbers. A wave number is simply the frequency of light divided by a constant. All right, the unit of wave number is inverse centimeters. That's how you're going to see the x-axis in infrared spectra. The wave number is the x-axis, the y-axis is the percent transmittance. All right. Now, every signal in an IR spectrum has three characteristics. All right, it has three characteristics: wave number, intensity, and shape. We're going to start off by exploring wave number. All right, so for every bond, the wave number of absorption associated with bond stretching is dependent on two factors. All right, bond strength and the mass of the atoms. All right, so bond strength and the mass of the atoms sharing the bond. Now, if we treat a bond like a vibrating string, we can actually explain this relationship through Hooke's law, and it's gonna look something like this. And I actually want to zoom in on that really quickly. All right, reduced mass right here, right? We said the two things that it depends on is mass and bond strength. Reduced mass is in the denominator. All right, what that means is smaller atoms are going to give bonds that vibrate at higher frequency. Let's write that down. Smaller atoms are going to give bonds that vibrate at higher frequencies, right? Awesome. Now, the bond strength, also called the force constant, is in the numerator. All right, bond strength is in the numerator. Therefore, stronger bonds will vibrate at higher frequencies. Let's write that down. Stronger bonds, all right, gonna vibrate at higher frequencies. Fantastic. Awesome. Now, if we look under the branch for wave number, which is one of the signal characteristics of IR spectroscopy, all right, wave number, all right, associated with bond stretching, it's dependent on the two factors that we talked about, bond strength and masses of the atoms sharing a bond. Now, some things that also have an effect on wave number are hybridization states and resonance, all right? So hybridization, you're going to want to compare, right, sp3 to sp2 to sp hybridization, all right? So for an example, if you compare an alkane to an alkene to an alkyne, all right, how do we predict which one is going to have a higher wave number? Well, we want to ask ourselves, all right, kind of basing it back on the fact that we know wave number is dependent on bond strength and reduced mass. If we look at an alkane, right, an sp3 hybridized carbon, an alkene, an sp2 hybridized carbon, and an alkyne, an sp hybridized carbon, all right, we're looking at a carbon that has single bonds, double bonds, or triple bonds. Which one of these bonds is stronger, a single, double, or triple? Obviously, a triple bond is the strongest bond. Alkyne has the strongest bond because of the triple bond. All right, because it has a stronger bond, it's gonna vibrate at higher frequencies. It's gonna have a higher wave number. Now, another thing that plays a role is resonance. All right, the important thing to remember here is the more conjugated a system, the more resonance hybrids one has, generally speaking, the lower the wave number. Here's a really good example, a ketone versus a conjugated ketone. All right, a ketone is going to show up at 1720, whereas a conjugated ketone, one that has a double bond near it, right, so resonance is at play here, is going to have a lower wave number. All right, this is another example here. Ester versus a conjugated ester. Same pattern that you see. Awesome, fantastic. Now, the second factor, the second signal characteristic of an infrared spectra is intensity. Now, in an IR spectrum, some signals are going to be really strong in comparison with other signals on the same spectra. That is, some bonds are going to absorb IR radiation very efficiently, while other bonds less efficiently. And the reason for this has a lot to do with this thing called a dipole moment. Now, a dipole moment occurs when there's a separation of charge between the two atoms that are bonded. It can be a full charge, as you see in an ionic bond, or a partial bond, as you see in polar covalent bonds. Dipole moments arise from this difference in electronegativity, and it's a measure in essence of the polarity of a molecule. All right. In other words, the dipole moment is an electric field surrounding a bond caused by the bond and acts kind of like an antenna for absorbing IR radiation. Now, as a bond vibrates, the distance between the partial charges is constantly changing, which means the strength of the dipole moment also changes with time. Now, since electromagnetic radiation itself is comprised of oscillating electric fields, the bond can absorb a photon because the bond's oscillating electric field is going to interact with the oscillating electric field of the IR radiation. So you have two oscillating electric fields, one that is a consequence of the bond of the atoms, and one as a consequence of obviously the IR radiation that are going to interact with each other. The efficiency of a bond at absorbing IR radiation therefore depends on the strength of the dipole moment. We can take a really good example. All right, carbon double bonded to a carbon versus a carbon double bonded to an oxygen and a carbonyl, for example. The carbonyl, the carbon double bonded to an oxygen, all right, has a better separation of charge. Obviously, you have one atom that is more electronegative than the other. Oxygen is more electronegative than carbon, which means it's going to have a greater dipole moment than the carbon double bonded to carbon, which has no electronegativity difference between the two atoms because they're both carbon. All right, that means the carbonyl has a greater dipole moment, and the oscillating electric field associated with the carbonyl group is much stronger. So when it interacts with IR radiation, it's going to produce a much stronger peak as consequence. The third signal characteristic that we're going to talk about is shape. All right, there are two main things that we discuss and that the David Klein Organic Chemistry book discusses that will have an effect on shape in IR, and those are hydrogen bonding and symmetric asymmetric stretching. With hydrogen bonding, it can result in a weakening strength, which can result in a broadening of a peak. Alcohol groups are a really good example of this, and you see that hydrogen bonding of alcohol groups sometimes is going to contribute to this broadening peak right within this region, and that's a signature for alcohol groups because of that hydrogen bonding. Now, as with symmetric asymmetric stretching, this can result in several peaks. Primary and secondary amines serve as a good example of this. Primary amine exhibits two signals, one at 3350 and the other at 3450. Whereas secondary amines actually just only show one signal. And you might try to, explain this, two hydrogens on the primary amine is going to give two signals. But that's actually an inadequate explanation of that. The reason for the appearance of two signals is better explained by considering that the NH2 group can vibrate in different ways. One way in which the stretching is in phase, symmetric stretching, and the other way where they are out of phase, asymmetric stretching. So good to remember, and we're going to see a good list of all the different kinds of functional groups and their IR signals in a second, but good thing to remember that our primary amine exhibits two signals within the region of 3350 and 3450, where the secondary amine will only exhibit one of those signals. Fantastic. Now, really quickly, here is a table. All right, here's a table. Ooh, that's a bad arrow. Here's a table of functional groups and their frequencies where you're going to find them on an IR spectra. This is really good to get accustomed and familiar with. In case your professor doesn't give you this table in your test, that's really up to professor, and it differs between professors. I had to remember this table when I took organic chemistry too. So the best way to kind of get familiar with this is do enough practice problems. Now, the IR spectra in general is divided into two regions as well. Anything before 1500 wave numbers is called the fingerprint region. And in this course specifically, we're not going to worry too much about looking at the fingerprint region. What we're going to worry about is everything above 1500 wave numbers. This is called the diagnostic region. All right. And this graph really quickly shows a really good way of where you're going to find double bonds, triple bonds, and single bonds, what wave numbers those fall under. But the best table is this one right here, where it gives you the functional group specifically and its frequency. All right. With that being said, I want to jump into a couple of practice problems now. I think that's the best way that we're going to understand everything we just talked about. So we're going to go ahead, we're going to start off with this first practice problem. Here what we want to do is match each one of these molecules to its appropriate IR spectra. All right, we're going to start one by one here. What we're going to do is we're going to start off by looking at a molecule. We'll start off with this one, and we're going to just kind of briefly discuss what we see here and what kind of signals this molecule would give. All right, this molecule is just a simple hydrocarbon. All right, so the only signal that we're really going to see in our diagnostic region of the IR spectra is the carbon sp3 to hydrogen bond. All right, and this is going to show up anywhere between 2900 and 3000 wave numbers. So we're going to look for a spectra where the only signal that we're seeing is between 2900 and 3000 for the carbon hydrogen sp3 bond. The only graph that shows this is this one right here, 2900 to 3000. This is a signature peak for hydrocarbons, sp3 carbon hydrogen bonds. It has this sort of like triplet a breakdown of the peak, but this is how you'll always see carbon hydrogen sp3 bonds. All right, so for that first molecule, all right, the proper diagram for it is C. This is kind of cut off. This is A, B, C, D, E, F, G. All right, so this first molecule is C. That's the IR spectra for the simple hydrocarbon, the simple alkane. All right, let's go ahead and look at our molecule 2. All right, this one not only has just normal sp3 carbon, all right, bonded to hydrogens, also has this double bond, so carbon sp2 to a hydrogen. All right, so what we're looking for here specifically is a peak between 2900 and 3000, all right, and also another peak at 3100, at 3100 inverse centimeters for that double bond, for that sp2. All right, the diagram, the IR spectra that best demonstrates that is this one. Look, we have our carbon sp3, all right, and we have this 3100 peak for the sp2. All right, so for this molecule, the IR spectra that relates to that is A. Fantastic. Let's look at our third molecule now. This third molecule has your normal, right, carbon, hydrogen, sp3 carbon bonded to your hydrogen. It also has this lovely alcohol group. All right, so we're looking for the 2900 to 3000 peak, right, for the normal carbon hydrogen sp3 bond, but now we're looking for a peak that's anywhere that's broad, right, because it's an alcohol group, between 3200 and 3600. The one that best demonstrates that is D. Here we have our sp3 carbon to hydrogen bond, and here's our broad alcohol peak between 32 and 3600. All right, so for this third molecule, all right, D. Now let's look at this fourth molecule. This fourth molecule is called anhydride, and it has, two carboxylate groups, okay? Carboxylate groups are going to be very broad peaks. They're going to be very broad peaks between 2200 and 3600 wave numbers. So that broadest peak that you see is going to be the carboxylate. Look at IR spectra E. It has this broad peak that goes pretty much from 2200 to 3600. That means that for this molecule, the IR spectra for it is E. Now let's look at our next molecule. This next molecule has your normal carbon sp3s, right, bonded to hydrogens. All right, so we're going to look for our classic 2900 to 3000 peak, but it also has a primary amine. All right, that means we're going to look for two signals between 3300 and 3450. Okay, so what spectra has our sp3 peak right here, and then two peaks for our primary amine between 33 and 3450. All right, that's going to be spectra F. Fantastic. And now if we look at this last molecule right here, All right, we have our normal sp3 carbons here bonded to hydrogen, and we also have this strong carbon oxygen bond, all right, in the form of a ester. All right, that's going to be anywhere between 17 and 1800. It's going to be a very strong peak. So we're looking for a very strong peak around 17, 1800. All right, this spectra has that strong peak. It also has our good sp3 carbon hydrogen peak. Fantastic. So this molecule's spectra is going to be B. All right, so that's how you want to attempt to answer this. Look at each molecule, identify what kinds of groups it has, functional groups it has, where you're going to see them, and try to find them in the appropriate IR spectra. All right, let's move on to the next problem. We want to rank each of the bonds, excuse me, we want to rank each of the bonds identified in order of increasing wave number. So we're going to go ahead for every one of these peaks, for every one of these bonds that the arrow is pointing at, we're going to give it the wave number of where we would find it. All right, so our alcohol peak right here, all right, anywhere between 32 3600 wave numbers, right? So we're going to give it the higher number, 3600 wave numbers. Fantastic. Now here we have a carbonyl. Carbonyls are going to be around 1720. All right. Now we have this NH bond. All right. It's going to be around approximately 3400. Awesome. Now this bond here is between a carbon and an oxygen, single bond. This is going to be around 1000 inverse centimeters. All right, then we have this where it's pointing right here at the sp2 carbon. All right, that's going to be around 3100. Fantastic. Now we have this carbon-carbon double bond right here. This is going to be around 1650. All right, and then our carbon triple bond is going to be around 2200 centimeter inverse. By the way, these are all functional groups, right, with wave numbers that are in that table we looked at earlier, right? I'm simply just giving them to you right now. Now we have all these numbers, so let's identify them in order of increasing wave number. All right, increasing wave number. So obviously, all right, the highest wave number is going to be this alcohol group right here at 3600, right? So OH, all right, is the highest wave number, followed by our NH bond at 3400, and next we have our sp2 carbon hydrogen. Awesome. Followed by our carbon triple bond to nitrogen. Fantastic. Followed by our carbonyl at 1720, and then our carbon double bond, and then last but not least our carbon oxygen. All right, so we've ranked them from in order of increasing wave number. This has the highest wave number. Our carbon oxygen at 1000 has the lowest wave number. Fantastic. All right, next problem. We got to do quite a few, all right? Now, this one says, and this is a really good question, identify how IR spectroscopy might be used to monitor the progress of the following reaction. So if you threw, all right, if you threw this molecule in the IR spectra, what kind of signals are you going to get? Well, you have, right, this double bond feature, all right, which relates to a carbon sp2 bonded to a hydrogen. All right, this is going to give a signal at 3100 centimeters inverse. All right, for the sp2 carbon to hydrogen bonds here. All right, now what about just the carbon double bond that's present there? Well, this is going to give a signal at 1650 inverse centimeters. Beautiful. Now, if you then put this starting molecule, all right, with some more reactants, right, hydrogen 2 and platinum, all right, after this reaction happens and finishes, all right, we want to throw the product into an IR spectra. We want to get the IR spectra for the product. All right, this product would not have any of these signals. It no longer has an sp2 carbon. It no longer has a carbon-carbon double bond. The only thing here is an sp3 carbon bonded to hydrogens, which is going to give us a 2900 to 3000 inverse centimeters. So if you're monitoring the reaction if you're monitoring the reaction, the progress of this reaction, the difference in the IR spectra that you're going to see is the 3100 centimeter peak and the 1650 centimeter peak are no longer going to be there for the end product. The end product is only going to have a 2900 to 3000 inverse centimeter peak for relating to just the carbon-hydrogen single bonds. Fantastic. Now, if we do the second problem B, let me just erase some of this so we can have more room. All right. Starting product is this right here. It has an OH group. All right, so you're going to see a broad peak between 32 and 3600 for the OH. And of course, there's some sp3, sp3 carbons bonded to hydrogen between 2900 and 3000. All right, now after the reaction progresses and you get products, you're no longer going to have that broad alcohol bond anymore. All right, instead, you're going to have a broad, strong signal at 1720. This relates to carbonyl. All right, they're strong signals at 1720. All right, so that's how you're going to monitor the progress of this reaction. When you no longer have the broad OH band between 32 and 3600, instead, you get a strong signal at 1720 for the carbonyl. Fantastic. Let's do two really quick concept questions here. All right. Which of the following is not true about electromagnetic radiation? All right. The first answer says frequency is directly proportional to wavelength. All right. The second choice says frequency is directly proportional to energy. All right. The third answer says wavelength is inversely proportional to energy, and E says none of the above. All right, so we're trying to find which one is not true. In order to answer this question, we need these two formulas. All right, remember we talked about the speed of light equals wavelength times frequency. All right, if you're trying to find from this formula a definition for frequency, we just have to divide by wavelength on both sides. So frequency equals speed of light over wavelength. Frequency is not directly proportional to wavelength. The wavelength is in the denominator where frequency is here up in the numerator, all right? They are inversely proportional, all right? Frequency and wavelength are inversely proportional. That makes A not true. But let's also look at the other answer choices just so we can have a conversation about them. This says frequency is directly proportional to energy. Here's the other definition where energy is equal to Planck's constant times frequency. This is another important formula you should know. All right, energy is in the numerator, so is frequency. Those things are directly proportional. So this is true. This says frequency is inversely proportional to wavelength. We just talked about that. That is true. D says wavelength is inversely proportional to energy. All right, our formula for energy is E equals Planck's constant times frequency. Let's replace frequency with this relationship, right? Because frequency also equals speed of light over wavelength. So now we can write energy equals Planck's constant speed of light over wavelength. All right, energy and wavelength are inversely proportional. Wavelengths in the denominator, energy in the numerator. These are inversely proportional. This is also true. So the only statement that is not true about electromagnetic radiation is A, frequency is not directly proportional to wavelength. All right, this one is false. Okay, 3 says, which of the following statements is or are true about the frequency of stretching vibration according to Hooke's law? All right, so this reminds us of, right, this formula that we had talked about earlier. I'm going to go ahead and write it out. Cool, right? This is bond strength. This is reduced mass. All right, it says that frequency is directly proportional to the strength of the bond and the reduced mass, directly proportional to both of those things. All right, that's not true, right? Because one's in the numerator and one's in the denominator. Frequency can't be directly proportional to both. That's not true. It's only directly proportional to the bond strength. It's inversely proportional to the reduced mass. B says that frequency is inversely proportional to the strength of the bond and the reduced mass. Both of these are incorrect, all right? They're stating that frequency is either directly proportional to both things or inversely proportional to both things. That is incorrect. Frequency is directly proportional to bond strength, and inversely proportional to reduced mass. All right, inversely proportional. C says frequency is directly proportional to the strength of bond. Finally, something that is correct. D says that frequency is inversely proportional to reduced mass. Finally, that's also correct. Both C and D are correct, so the answer choice is E. All right, always remember your formula right here. This is frequency. It's directly proportional to F. They're both in the numerator. Let's go back right there. Where were you? Here's frequency. Here's reduced mass. One's in the numerator, one's in the denominator. That means that reduced mass and frequency are inversely proportional, all right? And so C and D help communicate that. So both of those are correct. Fantastic. All right, so this question says, for the IR spectra depicted below, determine the principal functional groups present. All right, so we're only looking at 1500 and above here. Here's 1500. So we have two peaks. We have this peak and we have this peak. This one's really easy. We've talked about this a lot. All right, between 2900 and 3000, and it has like this wiggly line. All right, this is our carbon sp3 bonded to hydrogen. All right, and then this bond right here, strong signal at 1720. This is a carbonyl group. All right, and now this is the last question here for today. It says, for the following reaction, which of the indicated changes are consistent with the conversion of reactant to product? Let's look at the reactant. The reactant has carbon sp bonded to hydrogen right here. This is a sp carbon. It has a hydrogen right there. This is going to give us a signal at 3300 centimeters inverse. All right. And then it also has a carbon triple bonded to carbon. This is going to give us a 2150 inverse centimeter peak. All right. When it reacts with these, it changes. And instead, we're going to have just a carbonyl group right there. This carbonyl group shows up at 1720. So our IR spectra should go from having these peaks to just this peak. And the answer choice that demonstrates that is E. I hope that this was helpful. If you want to see more practice problems, you have specific questions, go ahead and leave them in the comments below or email them to me. My email is in the description box, along with a link to get the complete and the blank notes, as well as a transcript of this session in case you want to just read back over what was said instead of watching the whole video again. All right, all of that will be linked in the description box. I hope this was helpful. Happy studying and have a great day.